Okay, hi. So I'm going to be talking about functional categorization of objects using real-time markerless motion capture. Just before I start, I'd like to apologize for messing up with the schedule last Monday. Um, so just to get started, this paper is kind of similar to the one that Sam presented that day, in the sense that it also deals with object affordances in order to do object categorization and detection. So the goal of this paper is to do unsupervised categorization of objects in images and video, and of course, primarily based on functionality or affordance. So the motivation behind this is that sometimes this is more task relevant than categorizing based on appearance. For example, in autonomous robotics, and it has also been shown in psychological studies that human demonstration has an facilitative effect on categorization of objects in infancy. So one of the experiments that the paper mentioned is that infants were required to differentiate between objects, or rather, not required to, but were able to differentiate between objects better based on human demonstration, and they weren't able to do so as well when there was no human demonstration involved with those objects. So, what are the main contributions of this paper? They provide a new method for object categorization based on functionalities and affordances. They also have a novel approach for real-time pose tracking, a novel similarity measure for human motion. So we'll discuss later how they're able to distinguish between various action classes based on on this similarity measure. And they also came up with a new data set that helps them conduct a full series of experiments, which I'll talk about all of these in detail later. So the previous work in this field, there has been some work in the 90s where functional categorization was used, and the way that that was done was that objects were represented by functional parts, and then the shapes of those parts were modeled, and object categorization was done from there. Um there have been supervised approaches already that have annotations in the video of the object class and the motion class. Um, However, the difference from this piece of work is that in this piece of work is that there's no annotation of object classes or types of motion. It's all unsupervised. And there have been other works that also model object appearance based on the parts of the video that show motion similarity. So, for example, if you want to segment out the street in a busy city scene, then you could look at the similarity of human motion on the sidewalks, and segment out that portion because you have a lot of humans walking there as opposed to the street where you'd find cars. So the overview of this approach goes as follows. We start off with human pose estimation. From those pose estimates across various frames in the video, you can do temporal segmentation of the video into various poses. Yeah, and then you can use a series of poses to represent actions. So there's an initial segmentation of the poses, and then there's a clustering step where we define an action as a series of poses. And finally, using all of this information, we can do object localization and categorization. So let's start off with the human pose estimation bit. So the authors use a statistical model of the body, and this has 6 degrees of freedom for the torso, which is 3 translational and 3 rotational, and they also have 10 additional degrees for of freedom for the limbs. So we parameterize these degrees of freedom by capital theta. So I just wanted to point out that this is different from small theta, which we will also use later. So the skeleton that is parameterized in this way is surrounded by a 3D mesh of triangles on the surface of the body, and these are the points that are actually tracked in a video sequence. And in this paper, the height and gender of the person are assumed to be given, and those are used in order to morph the model 3D triangle points to the actual tracked 3D points on the surface of the human. So pose estimation is done from depth data, which is fairly low resolution, and the goal is to find the vertices vi prime of the 3D triangle mesh on the actual body, given the positions on the vi for a given pose and orientation of the bones that influence vi prime. So effectively, what this is saying is that every triangle mesh on the surface of the body is influenced by some set of bones k, by their orientation and their canonical position vi in the model. So that's how we get the formula that's listed there, which says that the vi prime, which is the real world 3D coordinates of a given triangle vertex, is some weighted some weighted combination of the model vertices, transformed by uh, uh, a transformation matrix for each bone k given its pose. So this is work that is taken from a fairly involved paper regarding capturing motion of humans in real time by Bregler et al. And the essence of this is that they use a representation called a twist uh, in order to estimate the parameters of the pose of a human. So the twist representation is it basically it takes a transformation matrix like a rotation plus translation matrix and represents it as a vector. So the epsilon that you see on this slide is a vector representation of say a 4 by 4 matrix, which ordinarily represents a transformation in three-dimensional space. Um, and so the goal over here is to be able to is to be able to compute the transformations tau theta, which we saw on the previous slide. And they show in that paper that this can be done by minimizing this this scary looking quantity at the bottom of the slide. So what is the overall pipeline that the authors use for pose estimation from depth data? They have three different channels of information that they use in order to find the 3D triangle mesh that we described earlier. The first is that they run hand and face detectors on this depth data. So that's the first image you see on the left. They also look at all the depth discontinuities of the image, which is the image in the middle. And finally, they look at model contours, which is on the right. So using all of these, they can get a set of correspondences. So here the green correspondences that you see are a result of the depth discontinuities. So this is effectively the data explaining the model. So every time you see a data point where there's a depth discontinuity, you try and match it to the model. The yellow points that you see are the model explaining the data. So here what we're trying to do is we're saying that every time we see a model contour, we try and find the corresponding depth point that is closest along the projection ray of that model contour. So those are the yellow points on yellow correspondences that you see. And finally, there are these red correspondences which correspond to um, the detections of the face and hands in the depth image. So having gotten all of these mesh vertices on the surface of the human, we can estimate the pose because it's an overconstrained problem. So you need at most 4 or 5 points to estimate a pose of a 3D object given its projections, but here we have so many more. Um, I'm sorry, scratch that. So we have many more degrees of freedom because this is an articulated object, but as you can see that we have a sufficient number of triangle meshes, triangle vertices, and so we can get a detailed estimate of the pose of all of the limbs that we care about. So moving on, now let's look at the initial temporal segmentation of the poses into actions. So the data set, I'll just describe the data set briefly here. So the data set consists of 6 subjects performing different actions such as pour liquid in a cup, drink with your left hand, etc. So there are a total of 13 action classes, and each subject performs a total of about 30 actions. So naturally some actions are repeated, but they're done on different objects which have the same functionality but um, uh, different appearances. So this is particularly to demonstrate the fact that we can learn object categorization from functionality rather than only from appearance. And each action is marked with a ground truth label. And finally, because we've already described a method for estimating pose, we just take all of the image data and store it as a sequence of poses in across time. So the authors use a technique called aligned cluster analysis for segmenting the motion capture data. The dataset was split into single action instances using this. So they mentioned that this is a very powerful tool for being able to split motion capture, and they don't go into a lot of detail, but they do mention that they are able to get a fairly well separated data set in the sense that they now have single actions being represented by a sequence of poses, and they want to use that information in further processing. However, one of the issues that ACA faces is that it is not able to capture the similarity in actions performed by different subjects. So, what this means is that you get a similarity matrix where there's a lot of poor similarity scores. So here, dark red means a poor similarity, whereas cool blue colors mean a good similarity score. So it's quite evident that action similarity is not really well captured by ACA. So in order to overcome this limitation of ACA, the authors came up with their own action descriptor so that they could model the similarity of actions performed even by different subjects. So the idea here is that they take as input all of the key or all of the poses that are in the data set, and they cluster them using k-means. So as you know, the poses are just a set of parameters that describe the triangle vertices, and you can cluster them in some high dimensional space. So they replace every pose eventually by the mean of the cluster that it belongs to, and then in any action sequence, whenever they find the same pose repeating itself in consecutive poses, they just remove all of those duplicates and replace it by just one pose. So effectively this leads to a variable length representation of every action, uh, which is a which is a set of poses. So you have an L dimensional vector where L is any number from 1 to infinity, and the elements of L are such that no two consecutive elements are the same. So this is the similarity matrix that's obtained after clustering is done, but before we remove the duplicates. So as you can see, you already get a much better similarity measure given that you clustered the poses. Um, and this is what you get if you remove duplicates in consecutive poses. So this is pretty good now because you have a high similarity metric between poses. So now that we've defined an action, we need a way to describe the distance between action, because we want to categorize objects based on their affordances. And using this variable length representation that we described earlier, we can come up with a similarity measure between two actions based on a variation of the Levenstein distance. So the Levenstein distance between two strings is just the number of operations that are required in order to make the strings the same. And a valid operation is either an insertion of some character, or deletion of a character, or a substitution of a character. So the modified version of the Levenstein distance that we're looking at is not just saying that any operation is the same, but weighting insertions, deletions, and substitutions depending on which poses are added to an action and which ones are removed or substituted. So to go into a little more detail with that, suppose we're trying to insert this character A or this pose A into a string of into the action where A and B are consecutive poses, and we want to put C in the middle. Then the weight Wi that would contribute to the Levenstein distance due to adding this C is the minimum of the distance between A and C and the distance between B and C. So this is formally stated in the formula below, where it says that the weight Wi for adding a pose P at position I um, to a pose sequence A would be the distance between P and the first element if you're looking to add the pose P at the first position. If it's any intermediary position, not at the extremes, then you take the minimum as is illustrated in the figure above. And if it is at the end, then once again you take the distance to the last pose in the sequence of in the sequence of poses. The story is quite similar for deletions. So once again, if you're deleting an element from the end or the beginning, then you just take the distance between the pose distance between the removed pose P and the next pose in the sequence. So if you were removing the first one, you look at the distance between the first pose and the second pose. If you're removing the last one, you look at the distance between the last and the second last one. And if you're removing anything in the middle, you look at the distance between the two poses that flank the one that you removed. And finally, for substitutions, you just look at the distance the two between the one that was substituted and the one that you used in place of it. So now that we have a distance measure between actions, we can discover the structure of the action data that we have in our data set in an unsupervised manner. So basically what this means is that we have a data set which is a set of a lot of actions, and we can look at clusters within this set of actions. So the method used for clustering different actions was hierarchical agglomerative clustering, and it was based on the average linkage between actions. And in this procedure of clustering actions, we discarded any set that contained less than three actions. So the reasons that the authors give for doing this is that any set with less than three elements was deemed not descriptive enough to constitute an action class. So finally, how can we do object localization and categorization given all of this action information? So object localization was performed as follows. The authors looked at the variance of hand position across the various frames of the video in 3D space, and then they assumed that the hand which has the highest variation across the video manipulates the object. And then with this assumption, what they do is that they create a mask of all the pixels that are within 250 millimeters of this hand, and do not belong to the human. And they discard any pixel that has very high temporal depth variance because they want to ensure continuity of the object. So effectively, the mask of the object across time is just all of those pixels that are close to the hand, but close together as well. So, what are some of the experiments that the authors did with respect to tracking, object tracking? I'm sorry, this is with respect to human tracking. They annotated some of the data with the ground truth and head and hand positions every 10th frame in the depth images, and they found that the human pose estimation yielded an accuracy of, or rather, yielded an error of about 85 millimeters for both without and with occlusions. So this is fairly accurate, I suppose, given that depth data is probably captured at distances of the order of meters. So with respect to categorization, the hierarchical agglomerative clustering approach actually depends on two parameters. So the first one is obviously the number of key poses that you use. So this is, if you recall, the number of clusters that we had in when we tried to create this dictionary of actions, um, and basically, if you have a very low number of key poses, that means that they're going to be sets of actions that are not very different from each other. So there'll be a high similarity between different actions, even across two classes. Um, but if you have a very high number of key poses, then that means that you start having an issue with um, too few actions within a given cluster. And the second cutoff is the second parameter that the clustering algorithm depends on is the cutoff threshold, which is just the level up to which smaller clusters should be merged into larger ones. And this, if you think about it, has a similar effect as the number of key poses. So there's some trade-off between discriminative ability of the action classes that you learn versus just not having enough descriptive power. So after some experimentation, they found that using 30 key poses was the best. And they also found out that the cutoff threshold was best chosen to be such that no more than 20% of the input data was left out during categorization. So how do we categorize an object as belonging to a given as belonging to rather so let's come to the object categorization later. Right now, how do we categorize a given action? um, so we already learned clusters for all of our actions, and we also know how to compute distances between the various actions. So let's say given a test action, we want to see what label we should apply to that. So what we do is that we compute the modified Levenstein distance that we described earlier from that test action to every action in our data set. So you can think of it as finding the distance between that test action and all the actions within a given cluster, and then doing that same process for that same repeating that same procedure across all clusters of actions. So once we've done this, we can assign the test sequence a class label corresponding to the cluster where it has the least average modified Levenstein distance. And then we define the score of this particular label C for the action A as the relative frequency uh, of observing that action in that particular cluster divided by the maximum possible frequency across all clusters. So let's say that we had 5 clusters and we found that the modified Levenshtein distance was minimal for cluster number 2. So we would look at the ratio of the action class that we of the action classes that belong in cluster 2, and divide them by the maximum ratio across of all those actions across all of the clusters, and then the highest score possible for that cluster would be uh, the that action class which gives the maximum value of the score. So what are the categorization results that we get? The subjects were asked to initially perform the tasks without holding the object of interest. So, for example, if the task was drink with left hand, they were actually asked to perform a motion of drinking but without any object or with the wrong object in the hand. And you can see, and we'll see later that the results that are obtained even when we do have the object in the hand are not very different than the ones you're seeing here. So here what's visible is the scores that are obtained, the scores that we described earlier that are obtained for these various tasks across the 6 different subjects. So you can see that whenever you get a perfect score, that means that this max and the numerator coincided. So we actually did assign the action to the correct cluster, as in the cluster where that action uh, was maximal in ratio as compared to the other clusters. So, how about localization and categorization? So, if you remember, we did a mask-based localization technique, and the object here for this experiment was deemed correctly localized if the intersection over union of the mask that they found overlapped the ground truth with more than 50%. The precision and recall obtained in this case was 83.9% precision and 75.6% recall. And by merging the outcome of this step with the categorization step, they obtained their unsupervised combined algorithm for categorization. So, as I was saying earlier, in this case, the subjects were actually given the object to hold and perform the action for real, and you can see that there isn't much difference in the performance that you get. Overall, on average, using localization only improves the performance by about 4%, and there are instances where uh, not having the object even leads to better performance. So, the point that the authors are trying to drive home here is that functionality or human motion associated with a given object is really a good cue for object categorization. So here are some of the extracted objects that you get out of this of the masking procedure. Um, and what's interesting here is that the appearance of many of these objects, even within a given class, is quite similar. Is quite different, but they're still able to categorize them correctly. So here the columns all correspond to assignments to the same object class. So in particular, the coffee mugs in the center are really different in appearance, but this algorithm was able to correctly classify them as all belonging to the same category. The same is true, I guess, for um, the calculators. So that's the rightmost column. Um, it's also interesting that the different phones that you see, the third column from the right, the landlines, for example, the third and the fifth instance are very different from the mobile phones, but they are found out to be in the same category because you do pretty much the same thing with both of them. So, in conclusion, objects were fairly successfully categorized using just human motion cues. And the authors state that you can use this information in conjunction with color data for better object detection in videos. So a finer categorization could potentially be obtained if you used a combined approach across these two. So yeah, that's all I had for present today. Um, yeah, if any of you have questions after watching this, please feel free to shoot me a mail or catch me at an office hour. My email address is vkanoria, that's VKANORIA at stanford.edu. Thanks, and once again, apologies for messing up with the schedule last